Welcome to the sleepy Milky Way. This is a place built for quiet wandering, a gentle corner of the cosmos set aside for those who wish to slow down, breathe deeply, and let the universe carry them somewhere far away from the noise of ordinary life. Here, we travel together through galaxies and nebulae, past spinning stars and ancient light, across distances so vast they make the worries of any single evening feel very small indeed. This channel exists for dreamers and curious minds who find comfort in the enormity of space, who feel at peace when reminded that the universe has been quietly unfolding for billions of years before any of us arrived and will continue unfolding long after we are gone. If you find yourself here for the first time, you are warmly welcome. If you have been with us before, it is lovely to have you back. Consider pressing that subscribe button if you would like to join this small and unhurried community of gentle explorers. People who come here night after night to rest their minds in the deep and the infinite, who find something nourishing in the simple act of listening to the universe described slowly and with care, the way one might describe a favorite landscape at the end of a long day. Now, settle in, let your shoulders drop, close your eyes if you wish, and simply listen. There is no rush, there never is out here among the stars. The stars themselves have been waiting for billions of years, spinning and drifting and shining with a patience that no human schedule can quite match. And tonight they are waiting for us in the same way, quietly, without urgency, with all the time in the cosmos to spare. Tonight, we turn our attention to something quietly remarkable, a question that astronomers and physicists have turned over in their minds for decades, examining it from every gentle angle, approaching it the way one might approach a strange and beautiful stone found on a beach, holding it up to the fading light and wondering about all the forces that shaped it across the ages. The question is this: what would happen in the most gradual and scientifically considered sense if the Earth were to pass too close to a neutron star? It is a question that asks us, first, to understand what a neutron star actually is, and that journey alone is rich enough to fill an entire evening. It asks us to think about how such an object comes to exist in the first place, sitting somewhere in the quiet dark of a galaxy, spinning with a patience and regularity that borders on the meditative. And then, having understood the nature of the thing, we can gently consider what its presence near our world would mean, tracing the slow cascade of effects from the outermost edges of the solar system inward, watching in the mind's eye as distance becomes closeness, and closeness becomes something that reshapes our understanding of what a planet truly is, what a world is capable of enduring, and what the universe looks like when two of its most extreme and beautiful objects find themselves briefly in the same small region of space. We will take our time with all of this. There is no urgency here, and none is needed. The universe itself moves in rhythms that dwarf our sense of hurry, and tonight we will try to match that rhythm as closely as we can. The question we are exploring is not one that requires anxiety or alarm. It is one that invites curiosity, that rewards patience, that becomes richer the more slowly you turn it over and examine its surfaces. So we will turn it slowly, in the quiet way that this channel always prefers. And by the time we have finished, it is my hope that you will have not only a deeper understanding of neutron stars and their remarkable physics, but a deeper sense of the universe as a place of unfolding process and quiet wonder. A place where even the most extreme events are part of a larger pattern that has been calmly evolving since before the first stars ignited in the primordial dark. Let us begin at the beginning, or rather, at one of the many beginnings that astronomers have traced as they have pieced together the story of neutron stars over the past century or so. Because the story of how we came to understand these objects is itself a beautiful one, full of patient observation and gradual illumination, full of moments where a strange signal in the data turned out to be something more profound than anyone had initially imagined. The history of neutron star science is, in microcosm, a history of how science itself works, how theoretical possibility becomes observational reality, how careful measurement accumulates into understanding, how the persistence of curious people working at the edge of what is known gradually expands that edge outward, one small and careful step at a time. For a long time, neutron stars were purely theoretical. They existed as mathematical possibilities, as objects that the equations of physics seemed to permit, but that no one had yet observed. The idea that a star could collapse into something so dense that it was composed almost entirely of neutrons, particles with no electrical charge, packed so closely together that the density of the resulting object would exceed anything found anywhere else in the ordinary universe. This idea was proposed in the early 1930s by physicists who were still working through the implications of quantum mechanics and the newly understood behavior of atomic nuclei. It was a bold proposition, made at a time when even the existence of neutrons themselves had only recently been confirmed by experimental work. The thought that a star, an object millions of times larger than the Earth, blazing with nuclear fire at its core, could leave behind after its death something so extraordinarily compressed and dense seemed almost too extreme to be real. And yet, the mathematics kept pointing in that direction, quietly and persistently, the way good mathematics often does, refusing to be dismissed, refusing to yield to the intuition that the universe simply would not arrange itself this way. The theoretical groundwork was laid by several physicists working in the extraordinary intellectual ferment of the 1930s, a decade that saw more fundamental changes in physics than almost any other. Walter Baade and Fritz Zwicky, two astronomers working at the California Institute of Technology, proposed in 1934 that a supernova explosion, then only recently recognized as a distinct and extraordinarily energetic class of stellar event, might leave behind a small, dense remnant star composed of closely packed neutrons. This was a remarkably prescient suggestion made in a short paper that has since become one of the classic references in astrophysical literature. At the time, it was received with interest, but also with a certain scientific caution, because the observational tools to detect such an object, if it existed, were not yet available, and the theoretical understanding of what such an object would look like, how it would behave, what radiation it would emit, how it would spin, was not yet developed. The idea settled into the scientific literature as a theoretical possibility, one of many exotic predictions that the new physics seemed to permit, and it waited there for several decades, patient as the objects it described, until the observations caught up. The theoretical understanding of neutron stars was developed in more detail in the late 1930s by the American physicist J. Robert Oppenheimer, later to become famous for a very different contribution to physics, as the scientific director of the Manhattan Project, working with his graduate student George Volkoff. Oppenheimer and Volkoff applied the equations of general relativity to the problem of a dense sphere of neutrons in hydrostatic equilibrium, deriving what is now known as the Tolman-Oppenheimer-Volkoff equation, which describes the structure of a neutron star and predicts a maximum mass for such objects, above which even the quantum pressure of neutrons cannot hold the object against further gravitational collapse. This maximum mass, the Oppenheimer-Volkoff limit, is now known to be somewhere in the range of 2 to 3 solar masses, though its exact value depends on the equation of state of dense nuclear matter, which remains one of the open questions of physics. The work of Oppenheimer and Volkoff established the theoretical foundation for neutron star astrophysics, and it remains one of the important contributions of that fertile era of theoretical physics, a piece of work whose implications continued to unfold for decades after it was first written. The universe, it turned out, had been making neutron stars long before anyone thought to wonder about them. They had been sitting in the galaxy all along, spinning in the dark, waiting to be noticed. And the way they were eventually noticed is itself one of the gentler stories in the history of science. A story about patience, about attention to detail, and about a young graduate student who refused to dismiss a puzzling irregularity in her data as mere noise. It is the kind of story that serves as a reminder of how science actually happens in practice, not always through grand eureka moments in well-funded laboratories, but sometimes through the quiet, persistent work of someone who simply pays very careful attention and trusts what she sees. In the mid-1960s, a radio telescope was being constructed near Cambridge, England, at the Mullard Radio Astronomy Observatory. A large and somewhat ungainly array of wire and wooden posts stretched across several acres of a field, designed to pick up radio signals from distant quasars, which were themselves newly discovered and poorly understood objects of great scientific interest. One of the people who helped to build it was a young woman named Jocelyn Bell, who was at that time working toward her doctorate under the supervision of the astronomer Anthony Hewish. Bell spent considerable time and effort helping to assemble the telescope, driving posts into the ground and stringing wire across the field in all weathers. And then, once it was operational, she took on the painstaking work of analyzing the paper charts that rolled out of it each day. Charts covered in the faint scratching of radio signals from across the universe. The charts arrived at a rate that required sustained attention. Bell later estimated that she was analyzing paper charts covering the equivalent of 400 feet of paper per week, and the work demanded not only intelligence and training, but a particular quality of attentiveness, a willingness to notice small things and to sit with them long enough to understand what they might mean. It was, in many ways, the perfect preparation for an important discovery, because important discoveries in observational astronomy often begin exactly this way, with someone paying attention to something that everyone else has overlooked. In July of 1967, Bell began her observations. Shortly afterward, she noticed something in the data, something she described with characteristic understatement as a piece of scruff. It was a small, unusual signal that did not look like the smooth radio emissions from quasars. It appeared intermittently, always from the same direction in the sky, and when she looked more closely at it, it seemed to have a regular, pulsed quality. as though something out there was switching on and off at a remarkably consistent rate. The signal had a period of just over 1 second, 1.3373011 seconds to be precise, and it repeated with a regularity that was, frankly, almost unnatural in its precision. The regularity was so striking that Bell and Hewish briefly and somewhat playfully referred to the source as LGM-1, where LGM stood for Little Green Men, because the signal was so perfectly regular that it seemed as though it might have been produced by something intentional, something that had chosen this particular timing deliberately, the way a beacon might. It was a moment of imaginative speculation that the team indulged briefly before setting it aside in favor of the more prosaic but more probable explanation that the universe was doing something interesting entirely on its own. But as Bell kept looking, she found more of them. 3 additional sources of similar signals coming from different parts of the sky. And this quiet multiplication of examples helped to rule out the more exotic explanations and to suggest instead something natural, something that the universe was doing all on its own in many different locations. By the time the discovery was published in the journal Nature in February of 1968, it was clear that Bell and Hewish had found a new class of astronomical object, something that was eventually named a pulsar, a portmanteau of pulsating and star. The discovery was genuinely historic, one of those moments when the map of the known universe quietly expands, when a door opens onto a corridor that leads to rooms no one had fully explored before. It is an interesting and somewhat melancholy note in the history of science that when the Nobel Prize in Physics was awarded in 1974 for this discovery, it was given to Hewish and to the radio astronomer Martin Ryle, but not to Bell, who had made the original observation. This decision was widely criticized by scientists at the time and has continued to be a subject of reflection in discussions about how scientific credit is assigned. Bell herself has responded to this situation with a remarkable degree of grace and generosity, and she has gone on to a distinguished career in astrophysics, receiving many honors in subsequent decades, including the Special Breakthrough Prize in Fundamental Physics in 2018, which she donated entirely to a fund supporting diversity in physics. The pulsar she found in 1967 continues to pulse quietly in the sky, as regular as it ever was, unaware of any of this. The question, of course, was what pulsars actually were. Various explanations were proposed in the period immediately following the discovery. Some scientists suggested that the pulses might come from oscillating white dwarf stars, vibrating at their natural frequency, while others proposed different mechanisms involving binary star systems or other exotic configurations of known objects. But over the months and years that followed, the weight of evidence and theoretical work converged on the explanation that we now accept as correct. Pulsars are rapidly rotating neutron stars. The regular pulses of radio emission arise because the neutron star's magnetic field is not aligned with its rotation axis, so that as the star spins, its powerful beam of electromagnetic radiation sweeps across space like the beam of a lighthouse. And each time it sweeps past the Earth, we detect a pulse. The faster the rotation, the more frequent the pulses. Some pulsars rotate hundreds of times per second. The fastest known pulsar rotates at more than 700 revolutions per second, a rate so rapid that if the star were any larger, it would fly apart under the centrifugal force, and only the extraordinary compactness of the neutron star allows it to spin so fast without disrupting itself. Some rotate just once or twice a second. All of them maintain their rotation with extraordinary stability, so stable that the most precisely timed pulsars are used as natural clocks of remarkable accuracy, rivaling and in some cases exceeding the precision of the best atomic clocks on Earth. With the discovery and identification of pulsars came a renewed interest in neutron stars as physical objects. What they were made of, how they were structured, how they came to exist, and what their presence in the galaxy meant for our understanding of stellar evolution and the ultimate fate of matter under extreme conditions. Over the decades since Bell's discovery, neutron stars have become one of the most studied and in some ways most beloved categories of object in astrophysics. Beloved not despite their strangeness, but because of it, because they represent a kind of extreme laboratory where the laws of physics operate under conditions that can never be replicated on Earth, and where the behavior of matter at densities beyond anything we can produce artificially offers clues to the deepest questions about the nature of the universe. Every observation of a neutron star is, in a sense, an experiment conducted at energies and pressures that no particle accelerator can reach, a probe of the physics of matter at its most compressed and most unusual, and the variety of neutron stars that observations have revealed: pulsars, magnetars, X-ray binaries, isolated cooling neutron stars, millisecond pulsars spun up by accretion from companion stars, ensures that there is always something new to understand, always another corner of the neutron star zoo that is revealing previously unnoticed behavior and previously untested physics. Let us settle into the physical description of a neutron star now, because it is genuinely worth taking time with. It is one of those descriptions where each additional detail seems to quietly enlarge the sense of wonder, where the numbers, though extreme, somehow make the object feel more real rather than less. The way a detailed portrait can make a historical figure feel more present. The physical properties of neutron stars have been determined through a combination of theoretical modeling, clever observational techniques, and in recent years, through the new tool of gravitational wave astronomy, which has provided independent and complementary measurements of neutron star properties that have both confirmed and in some cases refined the picture built up through decades of electromagnetic observation. The story of how we know what we know about neutron stars is as interesting as the knowledge itself. A neutron star is what remains after a massive star, a star much heavier than our Sun, typically somewhere between 8 and 20 or so times the mass of the Sun, though the exact range depends on the details of the stellar evolution and the mass loss the star experienced during its life, exhausts the nuclear fuel at its core and can no longer support itself against the inward pull of its own gravity. Throughout its life, such a star has been engaged in a kind of ongoing negotiation between gravity and the outward pressure produced by nuclear fusion reactions in its interior. Gravity pulls everything inward. Fusion pushes outward. As long as the star has fuel, this balance holds, and the star shines, sometimes for millions of years, sometimes for tens of millions of years, depending on its mass, because more massive stars burn through their fuel more quickly, like a very large fire that consumes its wood faster than a smaller, more modest flame. A star 10 times the mass of the Sun will burn through its hydrogen fuel in perhaps 20 million years. a long time by human measure, but brief on the timescale of the Sun itself, which has been shining for 4.5 billion years and has roughly another 5 billion years of hydrogen burning ahead of it. The most massive stars, those approaching 100 solar masses, may exhaust their core hydrogen in only a few million years, an eye blink in cosmic time. As the star evolves and exhausts the hydrogen in its core, it moves on to successive stages of nuclear burning: helium burning, carbon burning, neon burning, oxygen burning, silicon burning. Each stage shorter than the last, each stage occurring in the core, while the earlier stages continue in shells surrounding the core, producing an onion-like structure of concentric shells of different nuclear composition. Silicon burning, the final stage, produces iron, and iron is the terminus of the exothermic fusion chain. Iron is the most tightly bound of all nuclei, and fusing iron requires energy rather than releasing it. When the silicon burning phase produces an iron core of sufficient mass, approximately 1.4 times the mass of the Sun, a value known as the Chandrasekhar mass, the core can no longer be supported by the electron degeneracy pressure that has been holding it up since the silicon burning phase began. And what happens next occurs on a timescale that seems almost incomprehensible in its brevity. The collapse of the iron core to a neutron star is, in purely temporal terms, one of the fastest large-scale events in astrophysics. The core, which before collapse has a radius of perhaps several thousand kilometers, collapses to a radius of roughly 10 kilometers in a fraction of a second, perhaps a quarter of a second, perhaps a tenth of a second, depending on the mass and the microphysics. As the core collapses, the density increases until it reaches and then exceeds the density of atomic nuclei. At this point, the neutrons in the nuclei begin to behave as a macroscopic quantum fluid, and the repulsive component of the strong nuclear force between neutrons, which becomes dominant at very high densities, stiffens the core and halts the collapse abruptly. The core bounces, and this bounce sends a pressure wave outward through the infalling outer material, a wave that stalls initially as it propagates through the dense inner regions of the collapsing star, but is then revived by the enormous flux of neutrinos streaming outward from the hot, newly formed neutron star. The revived shock wave propagates outward through the star's outer layers and eventually blows them off in the supernova explosion, while the neutron star remnant sits at the center, hot and dense and spinning, left behind by the drama of the explosion, the way a stone is left behind when a wave breaks and recedes. The neutron star that emerges from this process is remarkable in every dimension. It typically contains somewhere between about 1.2 and 2 times the mass of the Sun, a mass which, in the case of the Sun, would fill a sphere more than 1.4 million kilometers across. But the neutron star's mass is contained within a sphere only about 20 kilometers in diameter. 20 kilometers. To put that in perspective, if you were to drive on a motorway at ordinary highway speeds, you could cross the entire diameter of a neutron star in less than 15 minutes. The entire mass of something heavier than our Sun, or perhaps nearly twice as heavy, compressed into something you could, in principle, drive across in the time it takes to listen to a few songs on the radio. The comparison is worth sitting with, not because it is meant to be dramatic, but because it is accurate. And accuracy here points towards something genuinely interesting about the nature of matter and the extremes that gravity can produce. The density that results from this compression is unlike anything else in the observable universe, except perhaps in the cores of black holes, which are hidden from direct observation behind event horizons, and therefore cannot be measured directly. A neutron star's density reaches approximately 4 × 10 to the power of 17 kilograms per cubic meter, a number so large that it is worth pausing with for a while, turning it over until it settles into something the mind can appreciate rather than simply register. A single cubic centimeter of neutron star material, a cube about the size of a sugar lump, would have a mass of roughly 400 million metric tons. The entire human population of Earth, all 8 billion of us, massed together in one place, would amount to only a fraction of the mass of a sugar lump-sized piece of neutron star. The entire Atlantic Ocean, with all its water, would be lighter than a teaspoon of the stuff. These comparisons may sound almost playful, but they are mathematically accurate, and they gesture toward something genuinely interesting. That the universe contains in these small spinning objects a form of matter so compressed, so different from anything we encounter in daily life, that it sits at the very edge of what our intuitions about matter and density are able to reach, in a region where only mathematics can reliably guide us. Inside the neutron star, the structure is layered in ways that physicists have been working to understand for decades, and some aspects of which remain genuinely uncertain. Not because of a lack of effort, but because the conditions in a neutron star's interior are so extreme that they cannot be directly replicated in any terrestrial laboratory. And so, our understanding must come from a combination of theoretical modeling, observations of neutron stars in various states and configurations, and the remarkable new tool of gravitational wave astronomy, which has recently begun to offer entirely new ways of probing what happens inside these objects. The neutron star's interior is, in a real sense, a natural laboratory for physics at the boundary of the known. A place where the theories we have tested in terrestrial settings must be extended beyond their normal domains of application, where new phenomena may exist that have no counterpart in any experiment we have yet conducted. The outermost layer of a neutron star is its crust, a region that is itself divided into an outer portion and an inner portion. The outer crust is composed of atomic nuclei arranged in a kind of crystalline lattice, nuclei that are increasingly neutron-rich as one moves deeper, increasingly stripped of the balance between protons and neutrons that characterizes ordinary atomic matter. In ordinary matter, atomic nuclei contain roughly equal numbers of protons and neutrons, the ratio determined by the balance between the strong nuclear force which holds the nucleus together and the electromagnetic force which repels the positively charged protons. But in the extreme pressure environment of the neutron star's crust, it becomes energetically favorable for protons to absorb electrons and become neutrons, a process called electron capture, and the nuclei become progressively more neutron-rich with depth. The electrons that would normally orbit these nuclei in ordinary matter are present here too, but they behave very differently from their counterparts in ordinary atoms, forming a kind of relativistic electron gas that threads between the nuclei and contributes to the star's overall pressure, carrying energy and momentum in ways that influence the star's thermal properties and electromagnetic behavior. As one moves deeper into the inner crust, the density increases to the point where neutrons begin to drip out of the nuclei altogether, a threshold known poetically as the neutron drip point. And beyond this point, there is a sea of free neutrons filling the space between increasingly exotic nuclear structures. These structures are thought to adopt a variety of geometries at different depths: spherical blobs of nuclear matter, then cylindrical rods, then slab-like sheets, then cylindrical holes in a sea of nuclear matter, then spherical holes, a sequence of shapes known informally as nuclear pasta because of a fancied resemblance to various pasta forms. The sequence from meatballs to spaghetti to lasagna to anti-spaghetti and anti-meatballs represents a beautiful example of how symmetry and energy minimization determine the structure of matter at extreme densities. And it has been the subject of detailed theoretical study and, more recently, tentative observational investigation through the way these structures affect the star's thermal conductivity and mechanical properties. Whether nuclear pasta actually exists in the crusts of neutron stars remains a question that current observations cannot definitively resolve. But the theoretical case for it is strong, and it represents one of the more quietly charming predictions of dense matter physics. Deeper still, in the outer core, the matter transitions to something that is thought to be a uniform fluid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. This is the region where the concept of neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which prevents any two neutrons from occupying the same quantum state, becomes the dominant force holding the star up against its own gravity. It is a remarkable thing to consider that the neutron star is supported not by any chemical or nuclear burning, not by heat or by light, or by any ongoing process of energy release, but purely by a quantum mechanical principle, by the stubbornness of particles that refuse to share a state. The star is, in a certain sense, an enormous expression of quantum physics writ at astronomical scale. A macroscopic object whose existence and structure are determined by the quantum properties of its constituent particles in a way that has no analogue in ordinary matter at ordinary densities. The neutrons in the outer core are thought to be in a superfluid state, a quantum mechanical condition in which the fluid flows without friction, without viscosity, without any internal resistance to motion. Superfluidity in laboratory settings was first observed in liquid helium cooled to temperatures near absolute zero, where the helium atoms all fall into the same quantum state, and the fluid acquires extraordinary properties. It flows through microscopic channels without resistance. It creeps up the walls of containers. It forms quantized vortices that rotate with a precision determined by quantum mechanics rather than by classical fluid dynamics. In a neutron star, the neutrons in the core are thought to form a similar superfluid, and the protons are thought to form a superconductor, a state in which electrical resistance vanishes entirely, allowing current to flow indefinitely without dissipation. These quantum states deep inside the neutron star affect the star's behavior in observable ways. The superfluid neutrons in the interior can store rotational energy in quantist vortices, and the exchange of angular momentum between the superfluid interior and the solid crust is thought to be responsible for a phenomenon called glitches. Sudden, small but measurable increases in the rotation rate of some pulsars, events that have been observed in hundreds of pulsars over the decades, and that provide one of the primary observational handles on the interior physics of neutron stars. When a pulsar glitches, it is as though the star's interior is periodically catching up with its crust, releasing pent-up angular momentum in a sudden transfer that causes the whole star to spin slightly faster for a period before gradually returning to its pre-glitch behavior. Watching a pulsar glitch is, in a real sense, watching the quantum mechanical interior of a neutron star express itself in the macroscopic world. The innermost core of the neutron star remains one of the genuinely open questions of modern physics. At densities exceeding even those of the outer core, densities that may be 5 or 10 times the density of ordinary nuclear matter, matter may behave in ways that our current theoretical frameworks do not fully describe. Some models suggest that the neutrons in the deepest interior break down into their constituent quarks, the fundamental particles from which protons and neutrons are themselves built, forming something called quark matter, or perhaps a color superconducting quark state in which quarks pair up in a manner analogous to the Cooper pairs of electrons in an ordinary superconductor, but governed by the strong nuclear force rather than the electromagnetic force. Other models propose the existence of hyperons, exotic particles containing strange quarks, such as lambda particles and sigma particles, that would form under the conditions of extreme pressure in the core, altering the equation of state in ways that affect the maximum mass of neutron stars and their observable properties. The existence of hyperons in neutron star cores has been a subject of considerable theoretical debate, in part because naive models, including hyperons, tend to soften the equation of state and predict a maximum neutron star mass lower than the largest neutron stars that have been observed, a discrepancy known informally as the hyperon puzzle, which remains unresolved and continues to motivate theoretical work. Still other proposals involve kaon condensates or pion condensates, or other exotic states of matter that are predicted by quantum chromodynamics, but have never been directly observed. The honest answer is that we do not yet know with certainty what occupies the very center of a neutron star, and this uncertainty is not a failure of science, but rather one of its most quietly exciting frontiers. A place where the known fades gradually into the not yet known, inviting further inquiry in the measured, careful way that good science always proceeds. The magnetic fields of neutron stars deserve extended attention because they are extraordinary in their strength and in the effects they produce, and because they will be central to our consideration of what a close encounter between a neutron star and the Earth would actually involve. When a star collapses to form a neutron star, any magnetic field that existed in the original star is compressed along with the star's material. And because the star's radius shrinks so dramatically, from something like the Sun's radius of about 700,000 kilometers to just 10 kilometers, the magnetic field is amplified enormously. This amplification follows from the conservation of magnetic flux. As the surface area of the star decreases by a factor of several billion, the magnetic field threading through that surface must increase by the same factor in order to conserve the total flux, and the result is a surface magnetic field that is billions or even trillions of times stronger than the field of the original star. Ordinary neutron stars, the ones we call pulsars in the conventional sense, have surface magnetic field strengths on the order of 10 to the power of 8 to 10 to the power of 12 Gauss, already vastly stronger than any magnetic field we can produce in a laboratory for sustained periods, and many billions of times stronger than the Earth's own magnetic field. But there exists a subclass of neutron stars whose magnetic fields are stronger still by factors of 1,000 or even 10,000. Objects called magnetars, which have surface magnetic fields estimated to reach 10 to the power of 15 Gauss or beyond. Magnetars are thought to form when the initial collapse produces a particularly rapidly rotating proto-neutron star, and the rapid rotation drives a convective dynamo mechanism in the neutron star's interior that amplifies the magnetic field to these extraordinary strengths during the first second or so after the collapse, before the star's rotation has slowed and the dynamo has ceased operating. The magnetic energy stored in a magnetar is so enormous, comparable to or exceeding the total energy radiated by the Sun in billions of years, that it can power outbursts of extraordinary violence. Sudden releases of energy in the form of X-rays and gamma rays that are visible from across the galaxy and sometimes from other galaxies entirely. A magnetar flare detected in the year 2004 from an object known as SGR 1806-20, located about 50,000 light-years from Earth, was so energetic that it briefly disturbed the ionosphere of our own planet despite that extraordinary distance. It is a detail worth pausing on. A star 50,000 light-years away briefly touched the outermost fringes of our atmosphere with its radiation, pressing briefly on the thin shell of ionized gas that separates us from the vacuum of space, leaving a measurable imprint on instruments around the world before the wave of energy passed and the ionosphere recovered its normal configuration. The universe, in its quiet way, is never entirely indifferent to us. The surface temperature of a neutron star immediately after its formation is extraordinary. The newly born star is hotter than almost anything else in the universe at that moment, its interior temperature reaching tens of billions of degrees, its surface glowing with X-ray radiation of a brilliance that outshines the Sun by many orders of magnitude at the relevant wavelengths. This initial heat comes partly from the collapse itself, which converts an enormous amount of gravitational potential energy into thermal energy, and partly from the nuclear reactions and particle interactions occurring in the first seconds and minutes after formation. But the neutron star begins to cool almost immediately because of a process that is, in some ways, the most exotic aspect of early neutron star cooling: the emission of neutrinos from the interior. Neutrinos are particles that interact with matter only through the weak nuclear force and gravity, which means they interact barely at all, passing through matter as though it were not there. A neutrino can pass through a light year of lead with only a modest probability of interacting with anything. In ordinary astrophysical environments, this near invisibility makes neutrinos of limited direct importance. But in the extraordinarily dense interior of a newly formed neutron star, even neutrinos cannot escape freely. They are trapped for a period of several seconds, during which they diffuse outward through the star, carrying the star's thermal energy with them. When they eventually escape, they carry away an enormous amount of energy, roughly 99% of the total energy released in the supernova, in a pulse that lasts for about 10 seconds. This neutrino pulse from a supernova was actually detected for the first time in 1987, when a supernova in the Large Magellanic Cloud, a nearby satellite galaxy of the Milky Way, produced a burst of 25 neutrinos spread among 3 detector experiments around the world. 25 neutrinos out of the 10 to the 58th power that were emitted actually interacted with the detectors. And this handful of particles was enough to confirm the basic picture of core collapse supernova and neutron star formation that theorists had developed over the previous decades. It was a quietly beautiful moment in the history of physics, a theory validated by 25 particles from an object 160,000 light-years away. After this initial rapid cooling phase, driven by neutrino emission from the interior, the neutron star enters a long phase of more gradual cooling, during which its surface temperature slowly decreases over millions and billions of years, emitting thermal X-ray radiation that can be detected by space-based X-ray telescopes. The rate of this cooling depends on the physics of the interior, on whether the neutrons and protons in the core have formed superfluids and superconductors, on whether exotic particles are present that provide additional neutrino emission channels, on whether the equation of state of the core matter is soft or stiff. By measuring the temperatures of neutron stars of known ages and comparing them with theoretical cooling models, astrophysicists can learn about the interior physics in ways that complement other observational approaches. The neutron star in the Cassiopeia, a supernova remnant, for example, a star approximately 340 years old, formed in a supernova that Chinese astronomers may have observed in 1680, has been observed to be cooling at a rate that has been interpreted as evidence for the onset of neutron superfluidity in its core, a genuinely remarkable measurement that offers a window into the quantum mechanical state of matter at nuclear densities. Now let us return to our central question with all of this context available to us, and approach the encounter between the Earth and a neutron star in a textured and careful way, tracing the effects at each distance, pausing to understand the physics at each stage, always maintaining the quiet, unhurried perspective that serves us best when contemplating things on scales that dwarf ordinary experience. The encounter we are imagining is a thought experiment, a way of exploring physical principles by following them to an extreme. And it is a thought experiment that reveals, by contrast, how delicate and fortunate is the situation in which our planet currently finds itself, orbiting quietly in a galaxy that is full of neutron stars, but has so far kept them all at a comfortable distance. The solar system extends much farther than most people intuitively appreciate, and understanding its full extent is important for understanding at what point a passing neutron star would begin to have effects. The 8 planets and their moons, along with the asteroid belt and the scattered objects of the Kuiper belt, occupy a region that extends to roughly 50 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. The orbit of Neptune, the outermost planet, lies at about 30 astronomical units from the Sun. The Kuiper belt, a band of icy bodies beyond Neptune's orbit, extends from about 30 to about 50 astronomical units. But beyond the Kuiper belt, extending outward to perhaps 50,000 or even 100,000 astronomical units, roughly 1 to 2 light-years, lies the Oort cloud, a vast, diffuse swarm of comets and icy bodies that represent the outermost boundary of the Sun's gravitational influence. The Oort cloud is so far from the Sun that its members are only loosely bound, perched at the edge of the Sun's gravity well, subject to perturbation by any passing mass. They are, in a very real sense, the most vulnerable part of the solar system, the first region to feel the gravitational influence of anything passing through the Sun's neighborhood. If a neutron star were to approach our solar system from interstellar space, traveling at a typical speed for stellar objects in the galaxy, which is several tens of kilometers per second, relative to the local standard of rest, or possibly much faster if it received a natal kick during the supernova that created it. The first region it would begin to influence would be precisely this outer Oort cloud. A neutron star's total mass is typically between about 1.2 and 2 times the mass of the Sun, which means its gravitational influence at large distances is broadly comparable to that of another star passing nearby. Stars do occasionally pass relatively close to the solar system on the scale of geological time, not through the inner solar system, but close enough to disturb the Oort cloud, nudging some of its inhabitants onto new trajectories, occasionally sending comets cascading inward toward the Sun and the inner planets. It is thought that the occasional increase in the rate of comet impacts on the inner planets, which the geological and lunar impact records suggest may have occurred periodically in Earth's history, may be related to such stellar passages perturbing the Oort cloud. A neutron star at these large distances would behave broadly similarly to any other stellar mass object passing nearby, with its gravitational influence stirring the outermost reaches of the solar system in ways that would unfold over thousands or millions of years. The cometary inhabitants of the Oort cloud gradually responding to the new gravitational perturbation, some finding their way onto trajectories that would eventually carry them into the inner solar system over timescales of thousands to millions of years after the encounter itself. But as the neutron star's passage brought it closer, not merely past at a distance of several light years, but actually through or near the solar system, the character of the encounter would begin to change significantly. The orbital dynamics of the Kuiper belt would be substantially disturbed. The Kuiper belt, which extends from about 30 to 50 astronomical units from the Sun, contains hundreds of thousands of icy bodies, the source of short-period comets and some of the most ancient unaltered material in the solar system, remnants of the original nebula from which the planets formed, preserved in cold storage in the outer solar system for the 4.5 billion years since the solar system assembled itself from its parent molecular cloud. A neutron star passing through or near the outer solar system would act on these bodies as a gravitational disruptor of considerable power, flinging some outward on hyperbolic trajectories that would take them permanently out of the solar system and into interstellar space, drawing others inward on trajectories that would eventually carry them past the planets. The comet showers that would result, arriving at the inner solar system over subsequent thousands of years, would be on a scale unlike anything that has occurred during the stable period of the solar system's recent history. The impact rate on the Earth and other inner planets would increase significantly, and the geological and biological consequences of this increased impact rate would be significant and long-lasting, unfolding over millions of years after the encounter itself had concluded. The outer planets, Neptune, Uranus, Saturn, Jupiter, would also begin to feel the gravitational influence of the approaching neutron star, and their orbits would be perturbed in ways that depended sensitively on exactly how close the neutron star's trajectory came to the Sun and how quickly it was moving. The solar system's orbital architecture, which has been remarkably stable for billions of years, maintained by the careful gravitational choreography of the planets and the dominant influence of the Sun, which contains more than 99% of the solar system's total mass, would begin to be rewritten. In the most general terms, a massive object passing through the solar system on a hyperbolic trajectory would exchange gravitational energy with the planets, potentially accelerating some of them and slowing others, nudging their orbits into new configurations that might take millions of years to fully develop, but would, in principle, affect every planet in the system. The precise orbital evolution would depend on the details of the encounter geometry and the speed of the neutron star, and it is something that can be studied in detail using numerical simulations of the gravitational many-body problem, simulations that astronomers have indeed performed for various encounter scenarios, finding a rich variety of possible outcomes depending on the parameters. Let us take a moment here to consider the neutron star's trajectory through the solar system in a little more detail, because it is worth understanding what kind of path such an object would follow and why. Any object moving through the solar system under the influence of the Sun's gravity will follow a conic section, an ellipse, a parabola, or a hyperbola, depending on whether its total energy, kinetic plus gravitational potential, is negative, zero, or positive. An object bound to the Sun follows an ellipse. This is the case for all the planets, for asteroids, and for comets on bound orbits. An object that arrives from interstellar space, not bound to the Sun, will have positive total energy and will follow a hyperbolic trajectory. It will approach from one direction, curve around the Sun, and then recede in a different direction, never to return. The speed at which it passes through the solar system depends on its initial speed in interstellar space, increased by the Sun's gravitational pulls as it falls inward. The closer it gets to the Sun, the faster it moves, in accordance with the conservation of energy. A neutron star arriving from interstellar space with a typical stellar velocity of perhaps 30 or 40 kilometers per second would be moving considerably faster than this by the time it reached the inner solar system, accelerated by the Sun's gravity as it fell toward closest approach. The encounter would be, in human terms, extraordinarily fast. The neutron star would sweep through the inner solar system in a matter of weeks or months at most, its closest approach brief and its recession rapid. But the gravitational effects it would leave behind would persist indefinitely in the altered orbits of the planets and the disturbed architecture of the entire solar system. The effects on Earth specifically would depend critically on the details of the encounter, on the distance of closest approach, on the neutron star's velocity, on its trajectory relative to the plane of the solar system. Let us consider a spectrum of scenarios, moving gradually from the distant and relatively gentle to the close and more consequential, always maintaining our calm and measured perspective, always remembering that we are exploring a thought experiment that illuminates physics rather than describing something imminent. The universe has been kind enough to keep its neutron stars at a comfortable distance from us for 4.5 billion years. And tonight, we are simply imagining, as an act of intellectual exploration, what the physics would look like if that distance were dramatically reduced. At the most distant end of the spectrum, a neutron star passing through the outer solar system, beyond the orbit of Jupiter, perhaps at a distance of 10 to 20 astronomical units from the Sun. The direct effects on Earth would be primarily indirect and long-term. The gravitational perturbations introduced into the orbits of the outer planets would, over millions of years, propagate inward through the gravitational interactions among the planets, potentially affecting the Earth's orbital parameters in subtle ways. The Earth's orbit around the Sun is not perfectly circular, but slightly elliptical, and the shape and orientation of this ellipse change slowly over time due to the gravitational influences of the other planets. A set of periodicities known as Milankovitch cycles, which operate on timescales of tens of thousands to hundreds of thousands of years, and are associated with the long-term variations in the amount and distribution of solar energy received by the Earth that drive the ice ages and interglacial periods. A significant perturbation to the outer planets' orbits could, in principle, alter the character of these cycles, shifting their periods, changing their amplitudes, superimposing new periodicities on the existing ones, with consequences for the long-term climate of the Earth that would unfold gradually over millions of years. It would be a very slow, very gentle form of influence, not dramatic, not sudden, but cumulatively significant over geological timescales. The way a slight change in the angle at which light falls on a landscape can, over the course of hours, transform the character of the scene entirely. Bringing the neutron star closer into the inner solar system, inside the orbit of Mars, approaching the Earth's own orbit at 1 astronomical unit from the Sun, the effects become more direct and more immediate. The gravitational force on the Earth from the neutron star would begin to compete more significantly with the Sun's gravitational hold, and the Earth's orbit would be noticeably perturbed. A close gravitational encounter with a stellar mass object can, depending on the geometry and timing, either shrink an orbit or enlarge it, circularize it or elongate it, change its inclination or leave it unchanged. If the encounter delivered sufficient energy to the Earth's orbit, it could eject the Earth entirely from the solar system, giving it enough velocity to escape the Sun's gravitational well and sending it out as a free-floating planet, a rogue world drifting alone through interstellar space with no star to warm it. If the encounter was of the right character to inject energy into the orbit without ejecting the Earth, it might instead place the Earth on a much more elongated elliptical orbit, one that carried it alternately much closer to the Sun and much farther from it, exposing it to extremes of temperature and radiation that would be deeply challenging for any surface life. And if the encounter was particularly close, within a fraction of an astronomical unit, it might perturb the Earth's orbit so severely that the planet's future trajectory intersected with that of another planet, setting up a chain of gravitational interactions among the inner planets that could, over millions of years, lead to a collision or to the ejection of one or more planets from the solar system entirely. None of these scenarios unfolds quickly by human standards. The orbital mechanics work on timescales of years and centuries and millennia, and the cascade of consequences from a close stellar encounter would take millions of years to fully play out. But on the timescale of a human life, or even a human civilization, the most immediate and significant effects would not be orbital, but environmental. The consequences of the neutron star's radiation and magnetic field on the Earth's atmosphere, climate, and biosphere. These are the effects that would be felt most directly and most urgently, and they are worth tracing in detail. The radiation from the approaching neutron star would reach the Earth at the speed of light, far in advance of the gravitational effects of the encounter, and the character of this radiation and its effects on the Earth would depend significantly on the type of neutron star involved. An ordinary pulsar, a rotating neutron star with a magnetic field of perhaps 10 billion Gauss, emitting radio waves and a modest flux of X-rays, would be a much less immediately energetic radiation source than a young, hot neutron star with a stronger field, or a magnetar with its extraordinary magnetic energy reservoir. Let us consider the range of possibilities, beginning with the more ordinary and moving toward the more energetic. An ordinary radio pulsar at a distance of, say, 1 astronomical unit, the Earth-Sun distance, would be emitting radio waves and X-rays at levels that, while far stronger than any ordinary cosmic radio or X-ray source as seen from Earth, would be modest compared to the Sun's optical and ultraviolet output. The radio waves would not penetrate the Earth's ionosphere. They would be reflected from the ionosphere's lower edge, as many radio frequencies are. But the X-rays would be absorbed in the upper atmosphere, depositing their energy in the ionosphere and mesosphere. The ionospheric effects would be significant. The ionosphere would be intensely ionized, its chemistry altered, its normal layered structure disrupted in ways that would affect radio communications at various frequencies. Satellite communications, which rely on radio signals that must pass through the ionosphere, would be disrupted. The upper atmosphere chemistry would shift as X-ray photons dissociated nitrogen and oxygen molecules and produced reactive nitrogen compounds that cascaded downward into the stratosphere. The stratospheric ozone layer, which depends on a delicate balance of photochemical reactions, would be affected by the influx of reactive nitrogen compounds from above. These effects are quantitatively similar to, though stronger than, the effects that large solar X-ray flares produce during periods of intense solar activity. Effects that are well studied and that provide a useful baseline for estimating the consequences of a more energetic external source. A young, hot neutron star at the same distance would be a significantly more powerful X-ray source. Its surface temperature of several 100,000 to 1,000,000 Kelvin, producing a thermal X-ray emission that would be energetically comparable to or exceeding the Sun's total luminosity, but concentrated almost entirely in the X-ray band. The consequences for the Earth's atmosphere would be proportionally more severe. Deeper ionospheric disruption, more intense deposition of energy in the middle atmosphere, more severe destruction of stratospheric ozone by reactive nitrogen compounds. The surface ultraviolet flux, augmented by the degraded ozone layer, would increase substantially, with consequences for surface life that would begin to become significant at this intensity level. Photosynthesis, which drives nearly all ecosystems on Earth, would be disrupted as ultraviolet radiation inhibited the biochemistry of the phytoplankton in the surface ocean and the plants on land. The food chains that depend on photosynthesis would be stressed in ways that would affect biodiversity and ecosystem function globally. A magnetar at the same distance would be a qualitatively different situation. Magnetar outbursts, the sudden releases of stored magnetic energy that produce intense pulses of X-rays and gamma rays, would expose the Earth to radiation doses that, at sufficiently short distance, would be comparable to those from a nearby nuclear detonation in terms of their ionizing effect on the upper atmosphere. The ozone layer, as mentioned, would be severely depleted, not gradually, but in the course of hours during an intense magnetar flare. The direct effects of gamma-ray radiation at the Earth's surface, while significant, would be mitigated by the remaining atmosphere and by the fact that the most energetic photons are absorbed high in the atmosphere rather than reaching the surface directly. But the secondary effects, the altered ultraviolet environment, the disrupted atmospheric chemistry, the global changes in the radiation environment of the surface, would be severe and would persist for years after the flare, as the ozone layer slowly recovered through the ordinary chemical processes that maintain it. The Earth's magnetic field would be deeply involved in the encounter at all of these distances, and it is worth spending some time with this interaction because it is one of the most interesting and least appreciated aspects of the neutron star close encounter scenario. The geomagnetic field, generated by the dynamo effect of circulating liquid iron in the Earth's outer core, provides the primary shield against energetic charged particles from space. It deflects the solar wind around the Earth, confines the Van Allen belts of trapped radiation, and generally maintains the relatively benign radiation environment that complex life on Earth depends on. The magnetosphere that it creates extends thousands of kilometers above the Earth's surface in all directions, with the boundary on the sun-facing side typically located at about 10 Earth radii, roughly 64,000 kilometers, from the planet's center. As a neutron star approached, the magnetic field of the neutron star, even at large distances, would interact with the Earth's magnetosphere through several mechanisms. The most direct would be the pressure of the neutron star's magnetic field and any particle wind it was producing, which would push against the magnetosphere from the direction of the neutron star and compress it. The compressed magnetosphere would be a less effective shield against energetic particles, allowing more of them to penetrate to lower latitudes and deposit their energy in the upper atmosphere. Aurora-like phenomena would be visible globally rather than just near the poles, as energetic particles found their way into the atmosphere along the compressed and distorted field lines. The beauty of these phenomena, and they would, from a purely aesthetic standpoint, be extraordinary, would arise from exactly the same physics as the ordinary northern and southern lights, simply operating at a dramatically higher intensity and over a vastly larger fraction of the sky. At sufficiently close range, the interaction between the neutron star's magnetic field and the Earth's magnetosphere would become increasingly complex and dynamic. The interaction between two large-scale magnetic fields is not a simple matter of one pressing against the other. Magnetic field lines of different orientations can reconnect, snap apart, and reform in new configurations, releasing stored magnetic energy in the process, driving bursts of energetic particles into the upper atmosphere, powering sudden changes in the charged particle environment of near-Earth space. This process, called magnetic reconnection, is responsible for the most energetic space weather events we experience during solar activity. The large geomagnetic storms that can disrupt satellite operations, affect power grids, and produce dramatic aurora at low latitudes. In the context of a neutron star encounter, reconnection events between the neutron star's field and the geomagnetic field would be vastly more energetic than anything produced by solar activity, and their consequences for spacecraft, communications infrastructure, and potentially for the Earth's atmospheric chemistry would be significant. Now, let us turn to the gravitational tides in earnest, because they represent the most direct physical effect of the neutron star's mass on the Earth itself, and because the physics of tidal forces in the context of a neutron star encounter is particularly rich. Tidal forces arise from the differential gravitational pull of a distant body across an extended object. The near side of the extended object is closer to the gravitational source and experiences a stronger pull than the far side. For the Earth-Moon system, these tidal forces manifest as the familiar ocean tides, modest bulges in the ocean that follow the Moon as it circles the Earth, raising sea levels by a meter or two in the open ocean, and by much more in certain coastal geometries where the ocean's resonant behavior amplifies the tide. The Sun also produces a tidal force on the Earth, slightly less than half as strong as the Moon's, and the interplay of the two produces the familiar spring and neap tides of the tidal calendar. Tidal forces scale with the mass of the perturbing body and, inversely, with the cube of the distance to it, which means that doubling the distance reduces the tidal force by a factor of 8, and halving the distance increases it by a factor of 8. A neutron star with 1.4 solar masses at a distance of 1 astronomical unit from Earth would produce a tidal force on the Earth approximately 1.4 times that produced by the Sun at 1 astronomical unit. Significant, but not immediately catastrophic, producing tides substantially stronger than those currently driven by the Sun, but of a manageable character in terms of direct physical disruption. However, as the neutron star moved to smaller distances, the tidal force would increase rapidly. At 1/10 of an astronomical unit, about 15 million kilometers, well within the orbit of Mercury, the tidal force would be 1,000 times stronger than the Sun's current tidal influence on Earth, and at 1/100th of an astronomical unit, about 1.5 million kilometers, somewhat beyond the Sun's own surface, it would be 1,000,000 times stronger. At these extreme close ranges, the key concept becomes the Roche limit, the distance at which tidal forces overcome the self-gravity of the Earth, disrupting its structural integrity. The Roche limit for a body of given density depends on both the mass of the primary body and the density of the secondary, and the calculation gives a distance of roughly a few tens of thousands of kilometers for an Earth density body near a neutron star mass object. Inside this distance, the tidal forces would overcome the Earth's self-gravity, and the Earth would begin to disrupt. But even well outside the Roche limit, at distances of hundreds of thousands to millions of kilometers, the tidal forces would be sufficient to produce dramatic effects on the Earth's oceans, crust, and mantle. The oceans would respond first, since liquid water is mobile and deforms readily under applied forces. The tidal amplitude would grow as the neutron star approached, eventually producing tidal waves of extraordinary height. Not tsunami, which are driven by seismic events and propagate across the ocean, but standing tidal bulges that would grow as the tidal force grew, eventually reaching heights of kilometers rather than the meter or so of the present ocean tide. These great tidal swells would move around the Earth as the planet rotated relative to the neutron star, sweeping across the coastlines of every continent and ocean basin, inundating coastal regions that have no experience of flooding on such scales. The energy in these tidal motions would be immense. The energy dissipated by tidal forces in the Earth's oceans and solid body would appear as heat, warming the oceans and the crust from within, driving currents and mixing patterns in the ocean that would alter global climate in ways that would be difficult to model precisely, but would be significant in their consequences. For weather, for marine ecosystems, and for the distribution of heat around the planet. The solid Earth would not remain passive in the face of these tidal forces. The crust and mantle, though they appear solid and rigid on human timescales, are in fact capable of deforming under sustained stress. The slow drift of tectonic plates across the surface of the planet is itself a manifestation of this underlying plasticity. Under the intense and rapidly changing tidal stresses produced by the approaching neutron star, the crust would flex and buckle, and fault systems around the world, the great tectonic boundaries where crustal plates meet and interact, would experience sudden releases of accumulated stress in the form of earthquakes. These would not be isolated events, but something more like a global seismic awakening, with fault systems on every continent and in every ocean basin responding simultaneously to the new tidal regime, producing a sustained period of seismic activity that would far exceed anything in the historical or geological record. The Richter scale, calibrated against the earthquakes of ordinary tectonic activity, might not even be the most useful measure of what was occurring. The pattern would be less like individual earthquakes and more like a continuous vibration of the entire planetary crust, a ringing of the Earth like a bell struck repeatedly and from every direction at once. The volcanic response to the tidal stress would follow, as the tidal forces penetrated deeper into the Earth and began to work on the partially molten material in the upper mantle. Volcanoes are, in their essence, expressions of the pressure differential between the hot, partially molten material in the mantle and the cooler, more rigid crust above it. Tidal forces that altered this differential, particularly those that produced rapid and large-scale changes in the stress state of the crust and uppermost mantle, would trigger eruptions from volcanic systems that were already close to their eruptive threshold. Supervolcanic systems, the large magmatic systems like those beneath Yellowstone in North America, or the Campi Flegrei system in Italy, or the Taupo volcanic zone in New Zealand, would be particularly susceptible, their large reservoirs of partially molten magma responding to the altered stress regime with the kind of eruptions that, in the geological record, are associated with significant disruptions to global climate and biodiversity. But in the context of a close neutron star encounter, even supervolcanic eruptions would be relatively minor elements of a much larger and more comprehensive disruption. The atmosphere would be simultaneously subjected to the effects we discussed earlier: radiation, particle bombardment, ozone depletion, and to the direct gravitational and tidal effects of the neutron star's proximity. The atmosphere is, after all, a fluid layer surrounding the Earth, and it responds to gravitational forces much as the oceans do, though the restoring force, the Earth's gravity, acts somewhat differently on a compressible gas than on an incompressible liquid. Atmospheric tides exist even today, driven by the gravitational pull of the Sun and, to a lesser extent, the Moon. They are much smaller in amplitude than ocean tides because the atmosphere has a much lower density, but they are measurable and they affect global pressure patterns and wind fields in subtle ways. Under the influence of a nearby neutron star, these atmospheric tides would be amplified to the point where they produced significant effects on the large-scale circulation of the atmosphere. The jet streams, the Hadley cells, the monsoon circulations, effects that would manifest as dramatic and unpredictable changes in weather patterns across the globe, superimposed on all the other environmental disruptions already underway. The biosphere would be responding to all of these changes simultaneously, and the collective biological response to a neutron star encounter, while it is the most difficult aspect to model or predict with any precision, is perhaps the most poignant to contemplate. Life on Earth has survived remarkable perturbations across its 4 billion-year history. Mass extinction events driven by asteroid impacts, by volcanic eruptions, by glaciations, by changes in ocean chemistry. And in each case, life has persisted, diminished perhaps to a small fraction of its previous diversity, but always maintaining some thread of continuity that allowed, given sufficient time, a recovery and a subsequent diversification. The question of whether life would survive a neutron star close encounter depends entirely on the severity of the encounter, on how close the neutron star actually came, how long the encounter lasted in terms of the period during which conditions were severely disrupted, and on the pre-existing state of the biosphere at the time. Life is, in its quiet way, remarkably resilient, but every form of resilience has its limits, and the limits are tested differently by different kinds of stress. Deep ocean life, organisms living at the hydrothermal vents that dot the ocean floor, sustained not by sunlight, but by the chemical energy of the hot fluids emerging from the vents, would be the most sheltered from the radiation and atmospheric effects of the encounter, just as deep ocean life is thought to have been among the most protected from the effects of the asteroid impact that ended the Cretaceous period 66 million years ago. The vents themselves, driven by geological heat from the Earth's interior, would be affected by the tidal and seismic disruption of the encounter. But the basic energy source, geothermal heat, would remain available even through the most severe phases of the surface disruption. There is something quietly hopeful in this thought, that even in the most extreme scenario we have been imagining, the deepest and most ancient ecosystems on Earth, the ones most closely connected to the chemistry of the early Earth, might persist through the encounter and provide a seed for eventual biological recovery. The universe is patient, and so is life. As the neutron star reached its closest point in the encounter, its perihelion, the minimum distance from the Sun, and then began to recede, the tidal forces on the Earth would begin to decrease, the radiation flux would begin to diminish, the magnetic field interaction would gradually relax. The recession would be rapid in astronomical terms, weeks or months, and the immediate acute phase of the encounter would end. But the long-term consequences would persist for a very long time. The altered orbit of the Earth, if it had been significantly perturbed, would continue to carry the planet through a different thermal environment for as long as the orbit remained in its new configuration. And orbital perturbations of this kind can persist for tens of millions of years before being modified by subsequent interactions among the planets. The ozone layer, depleted by the encounter, would gradually recover over years to decades as the sources of reactive nitrogen in the stratosphere diminished and the ordinary photochemical processes of ozone formation re-established their balance. The seismic and volcanic activity would gradually subside as the tidal stresses were relieved and the Earth's interior returned to its pre-encounter configuration. The ocean tides would diminish back to their familiar modest levels. The sky, gradually clearing of the aerosols injected by volcanic eruptions, would slowly return to its familiar blue. And life, if it had survived, would begin the long, slow, patient work of recovery and adaptation that it has always done following any significant perturbation to the Earth's environment. Evolution does not rush, and neither does ecological recovery. But both are real, and both are remarkably reliable over sufficient time. The fossil record of the Earth, that long stone-written diary of life's history on this planet, shows a consistent pattern of disruption, followed by recovery, extinction followed by diversification, crisis followed by the quiet proliferation of forms adapted to the new conditions. There is no reason to think that the aftermath of a neutron star encounter would be different in this fundamental pattern, even if the details were unlike anything that has yet occurred in the Earth's actual history. There is something profound in considering the contrast between the neutron star, that small, impossibly dense, spinning remnant of a stellar life, and the Earth, that modest, water-covered, life-bearing planet orbiting a quiet yellow star in an unremarkable corner of a spiral galaxy. The neutron star represents the extreme of compression, of density, of the universe's capacity to pack matter into small spaces and subject it to conditions where the ordinary rules of chemistry and biology simply do not apply. The Earth represents the opposite extreme in some ways, a relatively low-density world where the conditions are mild enough that matter has had the opportunity to organize itself into the extraordinary complexity of living things. The contrast between these two kinds of object, the dead stellar remnant and the living planet, is a contrast that speaks to the breadth of the universe's inventory, to the range of forms that matter and energy take across the cosmos. Neutron stars are not truly dead, of course, in the astronomical sense. They spin, they emit radiation, they interact with their environments, they evolve over time, cooling, slowing, occasionally glitching, sometimes erupting in magnetar flares, sometimes accreting material from a companion star, and spinning up to millisecond rotation rates that are almost incomprehensible in their regularity. They participate in the universe's ongoing chemistry by forging heavy elements in their mergers. They act as cosmic clocks of extraordinary precision, helping astronomers to test the predictions of general relativity in conditions far more extreme than any terrestrial laboratory can achieve. They are, in their quiet way, among the most interesting objects in the cosmos, not despite their extreme properties, but because of them, because those extreme properties make them windows onto physics that is otherwise inaccessible. The story of neutron stars is also, in a deep sense, a story about our own origins. Every atom of iron in the Earth's core, every atom of gold in the Earth's crust, every atom of calcium in the bones of every animal that has ever lived on this planet was forged in a stellar interior or in a stellar death, in the cores of main sequence stars and red giants, in supernova explosions, in neutron star mergers, in all the varied and remarkable ways that the universe has of transmuting simple hydrogen and helium into the rich variety of elements that chemistry requires. We are downstream from neutron stars in a cosmic sense, the products of processes that included neutron star formation and neutron star mergers, our very substance shaped by events that occurred billions of years ago in parts of the galaxy that we have never visited and can never visit directly. The neutron star is not an alien object, a stranger to us. It is part of our genealogy, part of the long chain of stellar generations whose waste products and remnants accumulated into the interstellar medium, and eventually, in some quiet molecular cloud, condensed into our Sun and its family of planets. This genealogical connection to the stars, to neutron stars in particular, as the forges of heavy elements, is one of the more quietly moving insights of modern astrophysics. And it is one that gains in depth the more one thinks about it. When you pick up a gold ring and turn it in the light, you are holding matter that was assembled in the last moments before two neutron stars merged billions of years ago, in a collision that released more energy in a fraction of a second than the Sun emits in billions of years. The gold that was forged in that collision was scattered into the interstellar medium, mixed with other stellar debris, and eventually incorporated into the gas cloud that condensed to form the solar system. It has been part of the Earth since the Earth formed, locked in rocks and ocean sediments, occasionally brought to the surface by geological processes and collected by human hands, who attributed to it a beauty and a value that, in a different light, can be understood as a kind of unconscious recognition of its extraordinary origin. The universe has been generous to us in ways that are easy to overlook, and the gold in a wedding ring is one of its gentlest and most enduring gifts. The Milky Way itself, the galaxy in which all of this is happening, the galaxy that gives this channel its name, contains an estimated 100 billion to 400 billion stars, and among them, scattered throughout the galactic disk and the halo, are perhaps 100 million to a billion neutron stars in various stages of their long post-supernova lives. Most of them are old and cold and dark. Their radio emissions have ceased. Their surfaces have cooled below the temperature at which they are detectable with current telescopes. Their rotation has slowed to a few rotations per minute or less, and they drift invisibly through the galaxy, detectable only by their gravitational influence on nearby material. A small fraction are still active pulsars, emitting radio beams that sweep across the sky with each rotation, detectable from Earth if the beam happens to sweep in our direction. An even smaller fraction are magnetars, young and energetically active, their magnetic energy not yet fully dissipated, capable of the extraordinary outbursts that have occasionally reached across tens of thousands of light years to touch our ionosphere. The nearest of these objects, the nearest known neutron star, RxJ 1856.5-3754, at a distance of roughly 400 light-years, is, in galactic terms, practically a neighbor. 400 light-years sounds far, and by any human measure it is inconceivably distant. It is about 3.8 quadrillion kilometers, a number that renders linear distance essentially meaningless as a source of intuitive understanding. But on the scale of the Milky Way, which is about 100,000 light-years across, 400 light-years is a trivial distance, less than 0.5% of the galaxy's diameter. Our neighborhood in the Milky Way is, in this sense, well populated with neutron stars, even if their great distances mean that we feel none of their effects, and observe most of them only with dedicated astronomical instruments specifically designed for the purpose. The nearest active pulsars, those whose radio beams sweep in our direction and can be detected by radio telescopes, are at various distances, ranging from a few hundred to a few thousand light-years, and their radio pulses have been tracked so continuously and so precisely that astronomers have built up timing solutions for them that are accurate to microseconds over years of observation. This extraordinary precision is what allows pulsars to be used as natural clocks and as detectors of gravitational waves. Arrays of pulsars distributed around the sky can act as a galactic-scale gravitational wave detector, sensitive to the low-frequency gravitational waves produced by the inspiral of supermassive black hole binaries in the cores of distant galaxies. This technique, known as pulsar timing array astronomy, has in recent years produced what appears to be the first detection of a gravitational wave background. A sea of low-frequency gravitational waves permeating the universe, produced by the superposition of gravitational waves from countless supermassive black hole binaries across cosmic history. It is a remarkable development, using the radio pulses of spinning neutron stars as a detector for the space-time ripples produced by the mergers of billion solar mass black holes at the centers of galaxies, connecting the very small, the precision timing of a rotating stellar remnant, with the very large, the gravitational dynamics of the most massive objects in the universe. There is a quality to neutron star science that mirrors, in miniature, the quality of the universe itself. Everything is connected to everything else, across scales and across distances that seem too vast to permit connection, by physical laws that operate the same everywhere and at all times. The Pauli exclusion principle that holds the neutron star up against its own gravity is the same principle that prevents the electrons in the atoms of your body from all collapsing into the lowest energy state. It is a universal law, operating from the subatomic to the astronomical, connecting the neutron star and the human in a web of shared physics that is one of the more beautiful and quietly moving features of the universe as we understand it. The gravity that would distort the Earth in a close neutron-star encounter is the same gravity that holds the atmosphere on our planet and keeps the Moon in its orbit and determines the shape of the Milky Way's spiral arms. The radiation that the neutron star emits is the same electromagnetic radiation that warms our skin in sunlight and carries the light of stars across billions of years to our eyes. Everything is, in the end, made of the same few ingredients, subject to the same few forces, woven together by the same laws into the extraordinary variety of structures and processes and phenomena that make the universe the place it is. The question we began with, what would happen if Earth passed too close to a neutron star, has, in the course of this evening's wandering, led us through a great deal of physics and history and wonder. We began with the theoretical origins of neutron star science in the 1930s, moved through the quiet discovery of pulsars in a Cambridge field in 1967, explored the layered interior structure of these dense objects from crust to core, examined their extraordinary magnetic fields and their varied forms from ordinary pulsars to magnetars, traced the history of neutron star cooling and the new insights from gravitational wave astronomy. And then, with all of this context, walked slowly through the encounter scenario itself, from the distant stirring of the Oort cloud to the tidal disruption of the Earth itself, pausing at each distance to understand what the physics was doing and what the effects would be. It has been, as such journeys through physics often are, a journey that has expanded outward rather than contracted, beginning with a single question and ending in a much larger space of understanding. The universe contains within it, side by side in the same galaxy, objects as different as the neutron star and the Earth. The impossibly dense, impossibly energetic, impossibly hot remnant of a stellar life, and the gentle, water-covered, life-bearing world that is the only home we have ever known. That both of these things exist, that the same universe, governed by the same laws, produces both the neutron star and the living cell, the gravitational wave and the flower, the magnetar flare and the soft light of a winter morning. This is, perhaps, the most quietly remarkable thing of all. The universe is not a place of uniform extremity or uniform gentleness. It is a place of extraordinary range, a place where the same underlying principles express themselves in forms that span more orders of magnitude than the mind can comfortably hold, from the subatomic to the cosmological, from the briefest quantum fluctuation to the slow drift of galaxies across billions of years. And we, on our small and fortunate planet, have the extraordinary privilege of being able to think about all of it, to send our minds outward across the light years, to reconstruct from photons and gravitational waves and the mathematical language of physics a picture of the universe that, while incomplete, is genuine and growing and deeply beautiful. The fact that human beings, composed of atoms forged in stellar interiors and assembled by 4 billion years of biological evolution on a planet orbiting an unremarkable star, have managed to understand as much about neutron stars as we now understand. The fact that we have been able to detect their gravitational waves, map their thermal emission, time their pulses to microsecond accuracy, probe their internal physics through glitches and cooling curves and tidal deformability measurements. This fact is, in its own way, as remarkable as anything the neutron stars themselves do. The universe has produced, in us, something capable of understanding it, and this is a gift that feels worth recognizing on a quiet evening like this one. The nearest neutron star continues on its long drift through the galaxy, cooling slowly, its surface temperature dropping by fractions of a degree over human lifetimes, its rotation slowing by fractions of a millisecond per century. It is in no hurry, and neither are we. The galaxy is patient. The physics is patient. The questions we have not yet answered about the interiors of neutron stars, about the equation of state of dense matter, about the nature of quark matter, and the hyperon puzzle, and the superfluid state of the neutron star core. These questions are patiently waiting for the observations and the theoretical insights that will gradually illuminate them. The way a landscape is gradually illuminated at dawn, detail by detail emerging from the dark as the light gently strengthens. Tonight, you have traveled with us from the quiet laboratories of 1930s. Physics to the radio telescope array in a Cambridge field, from the theoretical structure of neutron star interiors to the tidal disruption of a living planet, from the first pulsar timing measurement to the gravitational wave background produced by supermassive black holes across cosmic history. You have held in mind objects smaller than a city that outweigh the sun, magnetic fields strong enough to alter the behavior of atoms, tidal forces that could reshape a world, and the deep connection between all of this extreme physics and the atoms in your own body. And you have done all of this at the pace that the universe itself seems to prefer. Slowly, thoughtfully, without rushing, in the company of the stars. As your eyes grow heavy and the thoughts of the evening begin to soften at their edges, let the image of the neutron star stay with you for a moment. That small, dense, spinning point of extraordinary physics, turning in the dark of the galaxy, pulsing its radio beam across the light years with the regularity of a cosmic heartbeat. It is, in its way, a companion, not a threatening one, not something that requires concern or alarm, but one of the many remarkable things that share the galaxy with us, that are out there in the dark right now, spinning and cooling and drifting, part of the same universe, subject to the same laws, made of the same matter, connected to us across the void by physics and by history, and by the simple fact of existing in this particular corner of a cosmos that is, for all its extremes, a deeply habitable and deeply beautiful place. Sleep well, gentle explorer. The Milky Way will be here when you wake, still turning, still full of wonder, still patiently waiting for you to come back and look at it again. The neutron stars are in their places, the pulsars are timing their pulses, the galaxies are drifting in their slow, majestic currents, and the universe is doing what it has always done, calmly unfolding, quietly evolving, gently expanding through the dark, carrying all of us, all of this, forward into a future that is longer and more extraordinary than any single evening can fully contain. Thank you for spending this night with the sleepy Milky Way. Until next time, rest deeply, dream widely, and remember that you are made of stars.